8.3, the pH scale. Okay, this is a number line, pH going from 0 all the way to 14. We will devise such a number line a little bit later in the notes. And let's take a look at some of the common items here. Battery acid, very acidic. Lemon juice, a little bit more than 2. Stomach acid, right around 2. Soft drinks, pH 3. Coffee, pH 5. Most of the foods that we eat are going to be acidic or slightly acidic. Very few foods, in fact, are basic, and basic is above 7. Pure water's also exactly 7. Detergent, seawater, hair remover, oven cleaner, those are all very, very basic. Another item that should be over here that's around pH 11 is bleach. Bleach is very basic. Self-ionization of water. Now, I don't mean to shock you, but water molecules just left on their own will interact with one another to form ions. And you can see that you have hydronium ions forming on the left and hydroxide ions forming on the right. So water molecules, and this occurs just simply because the water molecules are very polar. They're surrounded by other water molecules, and so a very, very small percentage of water molecules in just a pure glass of water will be doing this. Now, for simplicity's sake, we remove a water molecule from both sides. So if I subtract an H2O from the reactant side here and remove an H2O from the hydronium ion, I would get just the hydrogen ion. And you might remember from the notes earlier on that we use the hydrogen ion even though in actuality it's the hydronium ion. It's just a simplified way of referring to the hydrogen ion or the hydronium ion. Now, for pure water at 25 degrees Celsius, and we have to specify the temperature because at higher temperatures you'll have more water molecules interacting like this, and at lower temperatures you'll have fewer molecules reacting like this. So at a specific temperature, 25 degrees Celsius, we'll have a certain concentration of the hydrogen ion, and it will be 1 times 10 to the negative 7. Now, of course, you can't make the hydrogen ion without also making the hydroxide ion. So the hydroxide ion concentration will be exactly the same. We'll come back to these two numbers in just a minute. Ion product constant, and this will bring in what we know about equilibrium. If we were to look at the self-ionization equation that we just looked at and write an equilibrium expression for it, we can remove the water because remember, water is a liquid. So if we get rid of the water, we can rewrite our expression. Rather than calling it Kc, we call it Kw. And the W, of course, stands for water. Now, at 25 degrees Celsius, remember, we know the hydrogen ion concentration and the hydroxide ion concentration. If you were to multiply those two together, you might know the law of exponents. We would add together the exponents, so negative 7 plus negative 7 gives us negative 14. And this is a very important relationship when we're talking about acids. If we know the hydrogen ion concentration, well, whatever the hydrogen ion concentration is, we know it times the hydroxide ion concentration will always get 10 to the negative 14. As one goes up, the other would go down, but the product would always be the same. So that's the key idea. The hydrogen ion concentration and the hydroxide ion concentration are inversely proportional. Inversely proportional means as one gets larger, the other gets smaller. And it's a nice little graphic for that. So if they're equal to one another, and that would be a neutral solution, we have an equal amount of hydrogen ions and hydroxide ions. As it becomes more and more acidic, you have more hydrogen ions and less hydroxide ions. As it becomes more and more basic, you have less hydrogen ions and more hydroxide ions. This is the proportionality sign, if you're not familiar with that. A logarithmic scale is used to represent the hydrogen ion concentration. And this is the equation that we use. pH is equal to the negative logarithm of the hydrogen ion concentration. And we'll look at this equation in more detail in just a minute. The pH, the lowercase p, stands for the power that that tin would have to be raised to get the hydrogen ion concentration. Now the negative sign here is simply because if you were to put in the hydrogen ion concentration and take the logarithm of it, you would get a negative number. The negative sign here removes that negative number. So example. So if the hydrogen ion concentration was 4.7 times 10 to the negative 4, and if we were to plug that into our calculator, and don't worry about doing it right now, just let me walk you through it. So if you plugged in 4.7 times 10 to the negative 9, and then hit the logarithm key, you would get a negative 8.33. But the negative sign here tells us that we can make it a positive number. And that will always be the case when you take the logarithm of a number that's less than 1. And if you have a negative exponent, it's always going to be less than 1. You'll have a negative number. The negative sign here simply makes it a positive number. And really, the whole idea of using the logarithmic scale is to make it much more simple. So rather than saying the hydrogen ion concentration is 4.7 times 10 to the negative 9, we can simply say the pH is 8.33. That's just kind of an easier way of expressing it. Now the pH has no units. It's defined by this equation. The hydrogen ion concentration has units of molarity, but the pH doesn't. So there's no units on it. Now, of course, you're wondering, what about sig figs, Mr. Massey? Well, there is a rule for sig figs. However, don't be overly concerned about it. If you were to just write 2 decimal places for all your answers, you'll be fine. I'm not going to penalize you for that. But for those of you that would like to know, there is a rule for it. And the rule is the number of significant figures that we have in the number that we're taking the logarithm of is the number of decimal places that we'll have in our answer. So this has 2 sig figs. We'll have 2 decimal places in our answer. All right, now let's look at our calculators. Now I know some of you are going to be using your own calculators, maybe calculators on your phone. You'll have to make sure that you understand how to use whatever calculator that you're using. All that I'm going to be able to do is to help you use the calculators that I've made available to you. And those calculators are still available. So please, if you have been trying to stumble around with your own calculator and it's been a little problematic, you can come to school. There's calculators at school for you to come pick up. Just let me know and I'll make sure that they're there for you. But they should be in the front office, at least that's where they were early on in the semester. I'm sure they're still there. Anyways, on these calculators, this is the logarithmic key. And right above it, we have the anti-log key, 10 to the x. Now that's the key that everybody tries to use for scientific notation, which we'll talk about in a few minutes. That's not a scientific notation key. That is the anti-log key. If you were to take the logarithm of a number, and then if you were to take the anti-log of that number, you would get the number that you started with, and this is the anti-log. We'll use that in a second. So practice. So get out your calculator, and we're going to do this together. And please pause the video as needed. All right. If we take in your calculator, type in 1000, 1000, and then hit the logarithm key. When you hit the logarithm key, the answer will be 3. You might hit the if it wasn't that, you might hit the on button, the clear button, and try it again. 1000 is 3. And then if we were to take the anti-log of that, which would be the second function, the logarithm key, which activates the 10 to the x, you should get 1000 back. So make sure that you're able to do that. Okay. Now let's try something else. So type in 0.0025 and take the logarithm of it, and you should get a negative 2.60. Notice it's a negative number here. Now we're not doing pH right now, we're just practicing with logarithms. But if it was pH, that negative sign, we would remove it because the pH is the negative logarithm, which means we would remove that negative sign. Okay, now if we were to hit the anti-log of negative 2.60, we should get the number that we started with. So practice that a little bit. So you want to be able to put in any number, hit the logarithm key, and then hit the second function, anti-log, and it should give you back the number that you started with. Okay? Okay, now, scientific notation. Now, you learned this last year. This was right before, the math unit was right before the shutdown. So all of you had this once upon a time, but it's been a while since you did it. So here's a refresher for it. The EE key is what we use for scientific notation. We do not use the 10 to the x key. Now again, this is for these calculators. Other calculators, different. But for these, we would use the EE key. Though almost all calculators have an EE key, and that's the key that is advised to use. It stands for engineering exponential or exponent, but we just call it the EE key. All right, now how we use that.
Let's see how you enter.
Oh, I'm going to show you a video on this. It's 3 minutes long. It's a really good video. So sit back and watch.
Let's see how you enter numbers in scientific notation on the TI-30XA calculator. It's a relatively inexpensive calculator. There's lots of functions on it. Very useful. Let's use Avogadro's number as our example. How do you enter 6.0221 times 10 to the 23rd on this calculator? Well, you type 6.0221, you hit the EE key, and then you press 23. Notice I did not hit the multiplication key. I did not hit a 10 to the x key or anything like that. I hit an EE. Your display will read 6.0221, and then superscripted a little bit up will be a 23. And what this really means is you just entered 6.0221 times 10 to the 23rd. So in scientific notation, on this calculator, don't hit the multiplication key. And don't multiply it by 10 raised to some power. That will cause problems in certain cases. I will show you when we get into doing multiplication and division in scientific notation why it's a problem if you don't use the EE key. So get this burned in your brain. EE, scientific notation. Something else in this calculator, you can flip it in and out of scientific notation display and then standard, or what this calculator calls floating display. So let's say you have it in this notation. This is your standard or floating notation, 0.00789. Say you want to have the calculator automatically show it in scientific notation. Press the second key, that's the yellow key. I think of it as a temporary caps lock. That sounds weird, but what's going to happen is after I've pushed that second key, then the next button push will be a yellow function because it's a yellow button. On the 5, right above the 5 is the SCI. So if I press the 5 next, I'm not pressing 5, I'm really telling it to put it into scientific notation display. And as soon as you hit the 5, it changes the display. And it makes it 7.89 times 10 to the minus third. And see that little SCI comes up? That means you're in scientific notation display. Well, what if it's in scientific notation display and you want to put it back into floating notation? Press the second button again, and then above the 4 you have in yellow FLO. That means floating. Remember, that's the same as standard notation. So that means if you go second and then 4, you'll have all your numbers display in floating notation. And so it'll put it back in as 0.00789. Now keep in mind, floating notation is only used, if you force it into floating notation, it's only used when the number is not too big or not too small. In other words, Avogadro's number will not be shown in floating display in this calculator because it doesn't show enough digits. Make the number small enough, it will not be shown in floating notation.
Okay, now I will walk you through some of those type of problems. All right, so again, have your calculator out, and so let me walk you through this. So type in, now I have parentheses here just for purposes of making it easier to read, you do not need to use parentheses. I'm a big proponent of not typing in more keystrokes than needed. So you would type in 2.35. Now stop. As he said over and over again quite adamantly, do not hit times 10. That's what the EE key is for. So you would type in 2.35 EE, and if you look on the display, it'll move over a little bit, and then if you type in a 7, that'll appear as a little superscript. But we want a -7. So you would type in EE7 and then hit the change sign key, which is right next to the equal sign at the bottom here, or the equal key at the bottom here, times 5.42 EE3, and then hit equals. And you should get 0.00127. Now, if you're not getting that, pause the video, clear the calculator, and try it again. Then I'll walk you through it again real quickly. 2.35 EE7, change the sign, times 5.42 EE3 equals. Okay, now that is the number that's on your display. But let's practice bouncing that from standard notation to scientific notation and back again, as he pointed out, by using the second function, key 4 and 5. Key 5 will convert it to scientific notation. So on your display, if you have the 0.00127 still there, hit the second function and then 5, and it will become 1.27 times 10 to the -3. Of course, on your display, it's not going to say times 10 to the -3. It'll just have a little -3 as a subscript up here. And then, if you want to convert it back to standard notation, then you would hit the second function for FLO is for floating decimal point, but we can just think of it as standard notation, and it should bring it back to what we had at the beginning here. Okay, so please pause the video and practice this a little bit, because you're going to need to, this needs to not be an issue for where we're going. I'll put it that way. You need to be able to fairly easily type in numbers that have, or type in scientific notation. One thing before I go here, if your display, if a number has so many zeros that you have to stop to count the zeros, you always want to put it in scientific notation. Like this number here is right on the boundary of acceptable. If it was another 0 here, you really would want to have that in scientific notation. Again, that's a real good rule of thumb. If a number is so big, or so many zeros, either before the decimal point or after the decimal point, that you would have to stop to count the zeros, you want to use scientific notation. Okay, so let's do practice using logarithms. So remember, we did this a little while ago. pH was equal to the negative logarithm of 4.7 times 10 to the -9, and I gave you the answer. Let's try it. See if you can do it. So type in, so again, clear your calculator, type in 4.7 EE9, and then change the sign. So 9, and change the sign down here. And then hit the logarithm key, LOG. When you do that, you're going to get a number with a negative sign in front of it. But that negative sign here means that we can ignore that negative sign. So it gives us the 8.33. So again, please pause the video and practice this a little bit. And I encourage you to not ever type in the negative sign that's in front of the logarithm key. Simply ignore the negative sign that you'll see on your display. Makes things a bit easier. Okay? All right. Okay, now what is a logarithm? A logarithm is the exponent 10 would need to be raised to equal a given number. Meaning, if y is equal to 10 to the x, then if we were to take the logarithm of y, it would equal x, x being the number that 10 would need to be raised to give us y. All right, now let's look at a couple of real examples. Take the logarithm of 100, it would equal 2, meaning that we would need to raise 10 to the second power to give us 100. Or if you were to take the logarithm of 8.2 times 10 to the 4, it would equal 3.09, meaning we would have to raise 10 to the 3.09 power to give us 8.2 times 10 to the 4. Now the key idea of all this is when we look at the pH scale and its relationship with the hydrogen ion concentration. Now remember, the hydrogen ion concentration is molarity. You can see that every time we go down a digit, or I'm sorry, not down, up a digit, pH, from 0 to 1 to 2 to 3, the hydrogen ion concentration goes down by a factor of 10. So 1 divided by 10 is 0.1, divided by 10 is 0.01, divided by 10 is 0.001, etc. So as the pH increases, every whole number increase, we have what we call a 10-fold decrease in the hydrogen ion concentration. So that's the key idea here. For every 1 unit increase in pH, there is a 10-fold decrease in the hydrogen ion concentration. You might not be familiar with that term tenfold. It means by a factor of 10. So if you were asked what is the comparison of the hydrogen ion concentration from a solution that's a pH 1 to a pH 2, well, the pH 2 is 10 times less concentrated, hydrogen ion concentrated. If you were to compare a solution that had a pH of 4 to a solution that had a pH of 2, the pH 2 would have 100 times the concentration as pH 4, be 10 times 10, 100. Okay, now let's draw a number line that we saw at the very beginning here. So draw a straight line across here, 3 divisions. The center point will be our neutral position, and that's the hydrogen ion concentration of 10 to the negative 7. Of course, this is in molarity. And then on the 2 ends, be 10 to the 0. Now anything to the 0 power is 1. So that's just another way of saying 1, but being consistent here, raising 10 to a power. So 10 to the 0, 10 to the negative 7, and then on the other end, it would be 10 to the negative 14. Now remember our little diagram here. When you have more hydrogen ions than hydroxide ions, the solution is acidic. So anywhere between 10 to the 0 power and 10 to the negative 7, the solution is acidic. Anything between 10 to the negative 7 and 10 to the negative 14 is basic. Now remember, the exponents are negative. So even though the numbers are getting larger, the factor is going down tenfold. So every time we go from 10 to the negative 7, 10 to the negative 8, etc., we have 10 times less hydrogen ion concentration. Okay, now let's relate that to the pH scale. If we were to take the negative logarithm of 1, we would get 0. Take the negative logarithm of 10 to the negative 7. Remember, you would get a negative 7, but the negative logarithm, the negative removes that and makes it just 7. And take the negative logarithm of 10 to the negative 14, we would get 14. So there's the pH scale. Go from 0 to 7, the solution is going to be acidic. From 7 to 14, it's going to be basic. Okay, now I'm going to be giving you the 6 pH equations that we're going to be using to do calculations. I'm going to walk you through how to use each one of these, but for right now, just write these down. Now the first one we already know. pH is equal to the negative logarithm of the hydrogen ion concentration. Going in the opposite direction, if we were given the pH and we want to know the hydrogen ion concentration, well, that would be using the anti-log key, but we would need to put in a negative pH. So the hydrogen ion concentration is equal to the anti-log of negative pH. Now we can make the same relationships that we have here with the hydroxide ion concentration. So we have two more equations that are identical, except instead of the hydrogen ion concentration, it's the hydroxide ion concentration. So instead of pH is equal to the negative logarithm of the hydrogen ion concentration, pOH is equal to the negative logarithm of the hydroxide ion concentration. And the same for the hydrogen ion concentration, hydroxide ion concentration, and pOH. It's the antilog of negative pOH. And then remember Kw, the water ion constant, ion product constant. We multiply hydrogen ion concentration times hydroxide ion concentration, we'll always get 10 to the negative 14. 1 times 10 to the negative 14. And then the last one is, and if you remember, the pH of 10 to the negative 7 is 7, and that's a neutral solution. So if we had a neutral solution, the pH would be 7, the pOH would be 7. And as one goes up, the other would go down. We would always have the same sum of the two, and that's 14. So whenever we know the pH, if we just subtract that from 14, we can get the pOH. So these are the 6 equations that we're going to be using. Now I hope I kind of walked you through it enough so that you're not completely lost, but at the end of the day, we just need to be able to use these equations. All right, now I'm going to give you a little flow chart that'll make this a little bit easier, I hope. And it looks like this. Now the 4 corners are the key factors dealing with pH. So you have pH, the hydrogen ion concentration, the hydroxide ion concentration, and the pOH. And the arrows show you what equation you would use as you go from one to the other. So if I want to go from pH to pOH, I would subtract pH from 14 to give me pOH. And if I wanted to go from pOH to pH, I would subtract pOH from 14. So just follow the arrows and look at the equations, and it'll tell you explicitly what you need to do. If I was given the hydroxide ion concentration and I want the pH, you can see there's really 2 paths I could take. I could first convert the hydroxide ion concentration to pOH and then to pH, or I could go from the hydroxide ion concentration to the hydrogen ion concentration and then pH. It really doesn't matter which route you take as long as you get there. Though I will point out, depending upon the path that you take, the final answer will be slightly different simply because of rounding. That's all. So be prepared to see that your answers are ever so slightly different than the answer key that I may have prepared. And it's not that I'm right and you're wrong or vice versa. It's just we took different paths. Okay, now we're going to do some practice. So take a minute and copy this table down, and I'm going to walk you through how to fill in each of the missing components here. So pause the video and copy that down. I'm going to walk you through this as best I can using the little equation flowchart here. Now you likely will be able to read the equations I'll be referring to easier in your notes than you will here. Some of them are sideways. And the calculator down here, I'll be pointing to the keys to help you along. Please feel free to pause, rewind as needed. Also, as we go along here, you might find that the answers that you come up with in your calculator are slightly different than the numbers that I'll be putting in here. Don't worry about that. That it's just a rounding issue as we go along. You might keep the number that's on your calculator, whereas I'm rounding it when I put it into the table here. So if your answers are just ever so slightly different, don't worry about it. That's not an issue at all. All right, so let's start. Type in 0.0050. And then let's go right from the hydrogen ion concentration to pH, and that is this equation here, this arrow here. That will give you 2.30. Now let me point out the equation is negative logarithm of the hydrogen ion concentration. Now typing in the negative sign there is not necessary. As I think I said earlier, simply ignore the negative sign that you see on your calculator rather than going through the trouble of typing in negative. So if you just typed in the hydrogen ion concentration and hit logarithm key, you'll get a negative 2.30. Just ignore that negative sign rather than typing in the negative number. Okay, now we can go from pH to pOH by subtracting from 14, and that's this arrow here. Subtract pH from 14 to give us pOH. Now we can take the pOH and use it to calculate the hydroxide ion concentration. That's this arrow here. To do that, we're going to be taking the antilog of negative pOH. So in your calculator, you'll need to have the 11.7 be a negative number. So 11.7, and then this is the change the sign key down here. And then hit the second function logarithm. That's the antilog key, and that will give you 2.0 times 10 to the negative 12. Now please make sure you're typing in times 10. Don't type in EE. Use standard scientific notation. X times 10 to a power. Now the pH is less than 7, so this is an acidic solution. Okay, let's do it all over again. This time, the number that we're given, we'll need to use scientific notation. Now remember, we're going to be using the EE key for that. So this will be 3.3 EE, and then type in 10, and then change the sign. Remember, we never type in times 10. It's 3.3 EE, 10 negative. And then hit the logarithm key, and you'll get the pH, 9.48. Subtract that from 14 to give us the pOH. Then make that a negative number. Hit the second function, logarithm key, to give us the antilog. And that's 3.0 times 10 to the negative 5. The pH is less than, or I'm sorry, is greater than 7, so this is a basic solution. Okay, now for the next one, let's do it a little bit differently. Let's convert directly from the hydrogen ion concentration to the hydroxide ion concentration, and that's this arrow here. To do that, we're going to need to divide the hydrogen ion concentration into 1 times 10 to the negative 14. So go ahead and type in 1 times 10 to the negative 14, so that's 1 EE 14, change the sign on it. Then divided by 4.5 EE 4, and then change the sign on it, and then equals. And that will be 2.2 times 10 to the negative 11. Now, we can now go from the hydroxide ion concentration to the pOH, and that is this arrow here. So if we just simply take the logarithm of the hydroxide ion concentration, we'll get the pOH. Subtract that from 14, so now we're going in the opposite direction here. Subtracting pOH from 14 gives us the pH. The pH is less than 7, so it's a basic solution. Okay, so now let's kind of do the same thing again for the next one. So we're going to be going from the hydroxide ion concentration. Here in a second. Yeah, we're going to go from the hydroxide ion concentration to the hydrogen ion concentration. So this arrow here. So type in 1 EE negative 14. I'll stop saying that. I'll read it off as it should be read. You need to know to type in EE. So 1 times 10 to the negative 14 divided by the hydroxide ion concentration that we're given here, 6.8 times 10 to the negative 12, and that will give you 1.5 times 10 to the negative 3. We take the logarithm of that number, that'll give us the pH, subtract that from 14, give us the pOH. The pH is less than 7, so it's acidic solution. Okay, now for the next one, we're given the pH. Let's go from pH to the hydrogen ion concentration. So that's this arrow here. So we're going to be taking the antilog of negative pH. So type in 5.5, make it a negative number, hit the second function, logarithm key, that's the antilog, and that'll give you 3.2 times 10 to the negative 6. Now let's divide that number into 10 to the negative 14, 1 times 10 to the negative 14. So type in, so clear your calculator, type in 1 EE 14 negative divided by 3.2 times 10 to the negative 6. And that'll give you 3.1 times 10 to the negative 9. Then if we were to take the logarithm of that, we'll get the pOH, 8.50. The pH is less than 7, so it's acidic. Okay, and then last, we're given the pH, or the pOH. So let's go from the pOH to the pH by subtracting it from 14. That'll give us 11.90. And then let's go from the pOH to the hydroxide ion concentration, and that's using the antilog key. Here, lost it. So type in 2.1, make it a negative number. Hit the second function, logarithm, that's the antilog, and that'll give you the hydroxide ion concentration. And then we'll need to divide, well, there's two ways you could do it. You could divide that number into 10 to the negative 14, but I think it'd be easier to use the pH. Let's do that. So type in 11.90, make it a negative number. So I'm going to be using this equation here. So the antilog of negative pH will give us the hydroxide ion, or the hydrogen ion concentration, 1.3 times 10 to the negative 12. pH is greater than 7, so this is a basic solution. Wow, that was a lot of talking. Hope that you got that. You have another chart that looks just like this to fill out in your homework. And but for right now, that will be it. That is the end of notes.